Good morning, team. It's a new, bright, cheery day outside. We got some sun finally. We are ready for video number 5 in our series on acids and bases. And one of the meat and potato parts of acids and bases is how we measure the acidity of a solution, right? So I've got some solution. How acidic is it? How basic is it? Blah, blah, blah. You all know from earlier classes like introductory chemistry, we use pH to measure that. All right, so this whole video is going to cover some review of what you've probably seen on pH and where that comes from and how we're going to use that and track uncertainty for future problems later, because ideally we want to be able to take strong or weak acids, strong or weak bases, and be able to tell the pH of those solutions, which is obviously a measure of the hydronium ion concentration. So hey, here we go. Let's see where this all comes from. Let's start with pure water. All right, so that would be what we talked about earlier when I introduced in chapter 15 different types of equilibria, Ka, Kb. We did Kw, so let's look at that one more time and then show you where this concept of pH comes from. All right, so let's take a look at water and let's have pure water react with itself or autoionize. Let's take water here with another water molecule. Right? We're talking pure deionized water in this case. We can have, because it's amphiprotic, right? We can actually have that donate an H plus over. It's going to react with itself. And then this will lose. That's acting as an acid in this case. This is acting as a base in this case. And so we're going to end up with the hydronium ion and the hydroxide ion. So let's put the hydronium ion there. Let's put the hydroxide ion there. So we've got an equilibrium, so we can write an equilibrium expression. So pause the video, write the equilibrium expression for this. Let's change the color. Let's make that Kw. So we'll use the sub W for water autoionization. Let's take the products raised to the power of their stoichiometric coefficient, which is 1 in these situations. So that would be the concentration of the hydronium ion times the concentration of the hydroxide ion. And I have nothing in the denominator because they're both liquids, condensed phase. We're going to treat those as constants. So there's your equilibrium expression for the autoionization of water. Easy. And of course, I gave you the value for that last time as 1.0 times 10 to the minus 14th. Sometimes you'll see it as 1.00 times 10 to the minus 14th. As far as significant figures, it won't matter because we've mentioned K values typically have 2 or 1 significant figures. So we'll probably go with 1.0 in this case. But I want to show you where that comes from. At roughly room temperature, if we were able to go in and measure the concentrations of the hydronium ion and the hydroxide ion, which should be the same, right? They're in a 1-to-1 stoichiometric mole ratio, so those shouldn't have the same concentration for pure water at any temperature. So around room temperature, probably, anywhere from, depending where you are, we're Southern California here, so it gets pretty hot. Not right now, but it normally gets pretty hot, so we're usually above 20 degrees Celsius. But you probably range from 18 to 22 degrees Celsius in that range somewhere for room temperature. So at around room temperature, the concentration of the hydronium ion is equal to the concentration of the hydroxide ion, which is about 1.0 times 10 to the minus 7th molar. All right. So what we can do, if we plug those values in, we will get, that's where the Kw value comes from, right? So if we take those two values, so Kw will be equal to the two concentrations. So that'll be 1.0 times 10 to the minus 7th times 1.0 times 10 to the minus 7th, which is 1.0 times 10 to the minus 14, right? So that's where we get that constant from. And I personally will provide, you probably have that memorized after you do about 80 billion of these problems, but I'll give that to you on quizzes and tests. You don't have to memorize any K values of any kind. So we'll use 1.00 times 10 minus 14th. And again, every once in a while, you'll see me pop in a 1.00. I don't think that'll be necessary. 2 sig figs will probably be fine. So we can see those concentrations there. And where pH comes from, I'm going to set up on the next board. It's just an interesting way to take, because humans in general don't like thinking in exponential or logarithmic terms. We like to think linearly. I like to look at a value of 2 versus a value of 5. 5's bigger than 2. I got that, right? But if I look at something like, hey, 1.7 times 10 to the minus 12, is that bigger or smaller than 3.2 times 10 to the minus 10th? And you're like, oh God, negative exponents, my head. So we don't like thinking that way. So we're going to look at solution acidity two ways. We're going to look at purely as the concentration of hydronium ions versus hydroxide ions, with hydronium ions representing acid, hydroxide ions representing base. But that tends to be a little more challenging because we got to think too much, and we like to make it more simplistic. Thus, the invention of the pH system, which is going to give us a scale where we can think in linear terms, 10 versus 2 or something. It's a lot simpler. So let me set up the next board, show you how we can look at solution acidity in two different ways and why we use pH to simplify our lives and our brains. All right, guys, so the first way we're going to look at the question of is the solution acidic or is it basic is what I consider the harder way. You're going to love the second way with pH later. But what we're going to do is classify neutral versus acidic versus basic as, like I mentioned earlier, the hydronium ion versus the hydroxide ion concentration. So if I have a neutral solution, then those are going to be equal to each other. So the hydronium ion concentration will equal the hydroxide ion concentration. So that would be pure water, and that's why you hear people calling pure water neutral. Okay, and we can test for this in the lab with pH strips or litmus paper, and I'll talk about that after I finish. There's a reason I put these in specific colors. An acidic solution, you'll have more hydronium ions than hydroxide ions, so they're not equal to each other anymore. So in this scenario, for an acidic solution, the hydronium ion concentration will be greater than the hydroxide ion concentration. So all you got to do is know the two values, and if hydronium ion is bigger than hydroxide ion, boom, I got an acidic solution. So I can do that with basic as well. For a basic solution, the hydroxide ion concentration is going to be greater. So I can put it this way, which is representing the base. All right, pretty easy to do. So that's our way. All we have to do is know those two values. Now, how are we going to know those two values? Well, we're going to use the KW expression for that. Okay? So let's do this example here. Let's read through it and then pause the video and see if you can work it out on your own and then compare your value to my value. And let's see what happens. All right, did you get it done? So we've got a solution. Doesn't matter what the solution is. That's not the point for this particular problem. But let's say we have a hydronium ion concentration of 3.2 times 10 to the minus 5th molar. However, that was discovered in lab, maybe with a pH meter or something like that. It'd be pretty tough to do that using pH paper or litmus paper. Those are just generic tests. Like a litmus paper, you've got the blue colors. I wish I had some. I can't get into my lab right now. You've got blue litmus paper and red litmus paper. And if I put blue litmus paper into a solution and it turns red, that means it's acidic. All right? That's why I have that in red there. If you put red litmus paper into a solution that's basic, it turns blue, and that's why I have basic under blue. So a lot of times B, blue, basic, and then acidic is red. If it's a neutral solution, you really won't see a change in color. You can put red and blue in a neutral solution, they won't change any colors. So B, blue, basic, red is acidic for litmus paper. pH paper is a little bit different. You get, you have a reference of different colors, and you could actually get, rather than just saying it's acidic or basic, which is what a litmus test is, it's either acidic or basic or neutral. It doesn't really tell you a specific value. A pH paper will turn a particular range of colors, and you can compare that to a standard and see what the pH is. But we'll talk about pH in a little bit. All right, so how are we going to do this? We know the hydronium ion concentration. We need to know the hydroxide ion concentration. So let's pop this together, and those are related by KW. I know that KW is the hydronium ion concentration times the hydroxide ion concentration. Now, I'm not going to give you that. I'll give you the value, right? I'll give you the value of 1.0 times 10 to the minus 14th, sometimes 1.00 times 10 minus 14th. But if this is a constant, right? If I know the hydronium, I can solve for hydroxide. If I know hydroxide, I can solve for hydronium. It's a very simple algebraic problem. So let's isolate our variable. I know this. I know the hydronium. I know that. Let's solve for hydroxide. So let's isolate the variable. You ready? So the hydroxide ion concentration will be the Kw value over the hydronium ion concentration. So I really like it when you show that step. You may not need it for yourself, but remember, it's about who's reading it and can they interpret what you're saying. Is it clear to them? So you don't want to make somebody reading or grading your papers and work to do the algebra themselves and figure out what you did. It also is an insurance policy for yourself to not make mistakes. So if you have that there, maybe you screw up the math, you might get some partial credit on a quiz or a test showing that you know the setup. You just, fumbled your fingers on your calculator or something. So let's plug in our values of 1.0 times 10 to the minus 14th. Good to two significant figures in that scenario. Let's divide that by the hydronium ion concentration of 3.2 times 10 to the minus 5th. Remember, we don't have to use units in here. We'll just plug in the molarity when we're done. Let's pop this out. So we got two significant figures. So I'm going to jump this. I haven't done this. So I'm going to go 1.0 times 10 to the minus 14th. Check me in. Let me know if I screw it up. I don't know how you're going to do that on a pre-recorded video. In lecture, you guys are like, ooh, you screwed up, professor. This is what it's supposed to be. All right, I'm going to divide that by 3.2 times 10 to the negative 5th. Make sure you can get those exponents in on your calculator. For mine, it's the EE button, so it's second function EE when I plug in that scientific notation or exponential notation. So I get 3.125 times 10 to the minus 10. 3.125 times 10 to the minus 10th, and that'll be molar. All right, two significant figures, two significant figures, two significant figures, tracking it with that vertical dash line. Since this is closer to 3.1 than 3.2, I'm just going to leave it as it is, as 3.1 times 10 to the minus 10th molar. So that is the hydroxide ion concentration. Very easy to solve. If you know OH minus, you got hydronium ion. If you got hydronium ion, you got OH minus, because you always know the autoionization equilibrium expression of water and its value, the Kw value. So very simple. Now let's finish the question. Is it acidic or basic? So we know the two values. I know the hydronium ion concentration is 3.2 times 10 minus 5th molar. I know the hydroxide ion concentration is 3.1 times 10 to minus 10th molar. So now's where it goes, which one's bigger? Because I go, well, 10's bigger than 5, but it's 10 to the minus 10th and 10 to the minus 5th. So you got the negative exponent. So it messes with your head sometimes. You're going to really love, this is why in the next part of this, we're going to do pH, because I can compare, 2 to 5. But I know 3.2 times 10 minus 5th is bigger than 3.1 times 10 minus 10th. So I can safely write that the hydronium ion concentration, I'm running on a board, is greater than the hydroxide ion concentration. All right? So hydronium is bigger, therefore that makes this an acidic solution. So I'm going to put acidic there, and I'm going to put that in brackets. And we get tired of writing solution over and over, so you see an SOLN. That's a nice abbreviation for solution we'll run into. Okay, so since that's kind of a pain in the butt to do, comparing those negative exponents to each other, let's show you why the pH scale was invented. So let me pause it, write up a new board, and we'll review pH. All right, I'm back. I had a little thing. I had to go fix a couple of squeaky doors and have one of my daughters feed my barking dog that was hungry. So now those distractions are out of the way and those little noises in the background. Gotta love working from home, right? But I'm just going to make these videos. I'm not going to edit things out. I'm just making them real, just like my lectures, man. They're just going to happen live and you're going to get what it is. Let's take a look at this second way of looking at solution acidity. So pH, I think pretty much everybody's heard of that. But what that means is, I kind of joke around and the P, I say, to P on something mathematically is to take the negative log of it, right? So it's just a mathematical function. So think of the P function as the negative log, right? So if I'm going to take a P of something, or as I say P, I'm going to P on something, I'm going to take the negative log of this. So if a lot of times acids are looked at as far as, instead of hydronium ion, the hydrogen ion, H+, you'll see those interchangeably. So If I do the pH, then that means I'm going to take the negative log of the hydrogen ion concentration, which you'll see at the introductory levels in some general chemistry classes. They just leave it as H+, but really it's H3O+, because that H+ doesn't exist in water. Remember, the water is donating an H+ to another water, forming hydronium. So really we should look at that as the negative log of the hydronium ion concentration. Right? That's what pH is all about. And you'll see, I'll use this one, but I just want you to let you know you'll see them interchangeable. And that's why it's called pH and not pH3O. pH sounds better. That just means take the negative log of the hydrogen ion or hydronium ion concentration. And doing the logarithm, what's nice about the log, you gotta love logarithms. We get all those wonderful stupid log tricks. Log of A, B is log of A plus log of B, and log of A to the X is X log B. There's a lot of cool tricks you can do in logarithms. But a logarithm allows you to take a broad range of values and shrink it down. Because remember, we're looking at, if we're comparing the hydronium ion to the hydroxide ion, in our last problem, I think we have you could have 10 to the minus 10th versus 10 to the minus 5. I mean, you have these huge ranges. I could have hydronium ion concentrations of 10 to the minus 1 all the way to 10 to the minus 12, 13, stuff like that. It's a huge range. So by taking logarithms of that, it shrinks it down into a really nice scale. Most of the time you'll see between 1 and 14. You could do 0 to 14. And then I can just compare things like 7 to 3 or 3 to 1. And I can see really easily which one's bigger. It doesn't require thinking in terms of negative exponents. Now I can P on anything. So I could also do POH, right? So I could take the negative log of the hydroxide ion concentration. So POH is the negative log, and we're using the base 10 log, not the natural log, which is a base E log, of the hydroxide ion concentration. Hey, works out pretty nice. Now, there's a nifty little shortcut we're going to be able to use in a second. If you know, if we know the hydronium ion concentration, we always know the hydroxide ion concentration just by using the KW expression. But I can do a little shortcut here. If I know pH, I can always get POH and vice versa because of this nice little trick. Right? So if I have pure water, the concentration of hydronium ion is 1.0 times 10 to the minus 7. Okay? And the hydroxide ion concentration would also be 1.0 times 10 to the minus 7. So let's look at this. For pure water, remember these concentrations are equal to each other. That's why it's neutral. So if I take the negative log of this and I take the negative log of that, I'm going to get specific values. You ready? And there's a new set of uncertainty rules we're going to look at. So if I take the pH, will be negative log of 1.0 times 10 to the minus 7. And if I take the POH, which is the negative log also of 1.0 times 10 to the minus 7, isn't that convenient? So we're going to get the same answer. Pop that in your calculator, and when you take a logarithm, the number of significant figures in your concentration is the number of decimal places you're going to get in your answer. So this would give me a value, let me use the same color, of 7.00, right? Because I got two significant figures here. That's going to give me 2 decimal places in my answer. And same with the POH. Take the negative log of the concentration. I will get 7.00. We can write a cool little equation where we can say the pH of a solution plus the POH of a solution will be 7.00 plus 7.00. When we add, we're limited by decimal places. That will give me 14.00. This is slick because now if I know the pH, I can just subtract it from 14 to get the POH. If I know the POH, I can subtract that from 14 to get the pH. Just like if I know the hydronium ion concentration, I can use the Kw expression to get hydroxide, and I can do that back and forth. So you got these slick little tricks. I'm going to, on a board, I'm going to connect all these together, the hydroxide ion concentration, hydronium ion concentration, pH, and POH, in a nice little square to show you how to get from one to the other. Just remember, when you're doing the logarithms, you take the number of significant figures in the concentration, that's the number of decimal places you'll get in your answer. All right, team. So here's a nice little overview of what we've been talking about, putting it kind of pictorially. So we have 4 variables that look at solution acidity: the hydronium ion concentration, hydroxide ion concentration, pH, and POH. It's easier to think in these terms than these terms, but you can do whatever way works depending on the problem. This just shows you how to interconvert. You can go around the square any way you want. You just can't go diagonally. So I can't go from pH to POH to pH to OH minus directly. I can't go hydronium ion to POH directly. But if I have the hydronium ion concentration, I could go to POH by going to pH first and then to POH, or I could go from hydronium ion concentration to hydroxide ion concentration, then to POH. I can go different directions if I want to. So again, if I want to go from the hydronium and hydroxide ion concentrations and interconvert, just use the Kw equilibrium expression. All right. If I want to go from pH to POH, just use the fact that those added together equals 14.00 here. If I want to go hydronium ion to pH, I just take the negative log of the hydronium. Remember, to p on something is to take the negative log of it. If I want to go from OH minus to POH, take the negative log. Well, we haven't talked about if I want to go from pH to hydronium ion concentration or POH to hydroxide ion concentration. Well, all we're going to do is just flip this equation around, right? So if pH is the negative log of hydronium ion concentration, I want to isolate the hydronium ion concentration. So let's move the negative sign over. So we're going to get negative pH equals the base 10 log of hydronium. And if you look on your calculator and look at the inverse, if you look at the LOG button and look at the inverse of your LOG button, it's 10 to the x. Right? So if I take the 10 to the x to both sides, I could say that the hydronium ion concentration, if I want to isolate it, will be 10 to the negative pH, right? X being the negative pH. Move the negative sign over, take 10 to the x on both sides. So all I have to do is go 10 to the negative whatever my hydronium ion concentration, my pH is, and I got the hydronium ion concentration. Sweet, huh? And now the uncertainty rules are opposite. So when you take a logarithm, the number of sig figs in the concentration is the number of decimal places in the answer. When you take an exponent, 10 to the x or e to the x, the number of decimal places in the pH or whatever is the number of sig figs you'll get in your answer. So they're just reversed. A lot of people don't track that, but just to let you know. So same things here. If I want to isolate OH minus, if I want the OH, if I'm given the POH and I want the OH minus, that will just be 10 to the negative POH. Right? Very simple. So let's do one sample problem to finish off this particular video. And we're going to look, so 2 more things. We're going to look at the pH scale, and then we're going to do a sample problem, which I think I'll do first because we got this up on the board. That shows you how to interconvert from one to the other. So I'll give you a solution with a particular variable, one of these 4, and we can calculate all of the other ones. Get your calculators ready. All right, so here's a typical problem you might see on a quiz or an exam involving pH. Again, I could give you any one of those 4 variables we put on that little square we had, the pH square, and we can solve for the other 3. So in this one, we have a solution with a POH, right? A POH of 3.24. So that's the given variable. We can now calculate all the other 3. I can calculate pH, I can calculate OH minus concentration, and H3O plus concentration. But this only asks for the H3O plus, the hydronium ion concentration. So if you look at that square from the prior, about a minute ago, you can see we can't go across the diagonal. We can't go from POH to the H3O plus. We're going to have to either go from POH to pH, and then from pH to H3O plus, or we can go from POH to OH minus and then OH minus to H0 plus. Doesn't matter. Do you like going to that way or going this way? You're going to get to the same destination, right? We'll get the same answer. So I'm going to do the easy math. Personally, I'm going to go from POH to pH first, all right? So I know pH plus POH equals 14.00. That's something I would provide you on a quiz or test, right? So we can now rearrange this and solve for, we know this, right? We know this, we can solve for pH. So I know pH will be 14.00 minus the POH, which was provided for me. So I'm going to go 14.00 minus 3.24. Good to two decimal places. So we're going to get two decimal places in our answer. You could, some of you could probably do that in your head. I don't trust myself so much. I need my calculator. Right, so I'm going to get a 10.76 for that. So the pH of that solution is a 10.76. And once we're done with this problem, I'm going to talk about the pH scale and tell you, like, what does that number mean, right? When I get a pH value, what does that mean as far as solution acidity? That's how we're going to end this particular video, which is this is a longer video because we're doing a lot of review on pH from our introductory chemistry classes. All right, so that was our first step. Now I can take that pH value and go from that to the H3O+. So we know that pH is negative log of H3O+, and I want to solve for the H3O+, right? So my H3O+, hydronium ion concentration will be 10 to the negative pH power, and I know the pH, so I'm just going to plug that in there, right? So let's go 10 to the negative 10.76. And on your calculator, you got to find that inverse button, right? So for me, I got my LOG button right there, and so my 10 to the x is the inverse. So I got to go second function on my LOG button to get the 10 to the x on there. So I'm going to go second function of the LOG to give me 10 to the x, and then I'll go negative 10.76. Different, you might have a different calculator. It all depends. Figure it out before the quiz and the test. That's what the homework's for. All right. So I have two decimal places in my 10 to the x term, which means I'm going to get two significant figures in my answer. And I get 1.737 times 10 to the negative 11 molar. Two decimals gave me the two sig figs there. That's closer to 1.7 than 1.8, so I'm not going to round that up. I'll keep it as 1.7 times 10 to the 11th molar. That is your hydronium ion concentration. So a little significant figure, tracking uncertainty information there, lots of review. So let's do one more part of this video and talk about the pH scale, which if you're more into biology and stuff, you've seen that plenty of times. All right, team, let's finish off this section on solution acidity and the pH value and pH scale. So if we look at this, because we can look at solution acidity as the hydronium ion versus the hydroxide ion concentration, but you get these crazy negative exponents. So by taking the negative log of it, so you take the log of, say, 1.2 times 10 to minus 5, that's a number much smaller than 1. When you take the logarithm of a number smaller than 1, you get a negative value. That's why we have the negative sign in front of it. So the pH is negative log of the hydronium. So it gives us positive values. And then the smaller the hydronium ion concentration, because we're taking 10 to the negative log, the higher the pH is. So what that translates into, high pHs tend to be lower hydronium ion concentrations, which are basic solutions, okay? Whereas higher concentrations of hydronium ion give you smaller pH values, right? Now again, pH value of 7 is true neutral. Right? So if you take the hydronium ion concentration of 1.0 times 10 to minus 7 for pure water, and you take the negative log of it like we did, we get a 7.0. So that's pure neutral. So anything below that is considered acidic. So remember that. pH is below 7 are acidic. pH is above 7 are basic. And it ranges from about 0. You don't see too many near 0. Sometimes you'll see 1 to 14. But up in the 14 range, you get the strong bases, things like bleach, lye, which is, like sodium hydroxide. That's what they called it back in the old days. Antacids, right? So you have your Thanksgiving meal. You're like, oh, man, not feeling too good because I got too much stomach acid going on, which is way down here, the low pH with strong acids. Yeah, you're going to take, some people take antacids to counteract that and neutralize that. Seawater, slightly basic. I think your blood, I'm not a biochemistry person, but I think blood is slightly basic as well, just barely. Um, Urine is a little bit acidic. Don't drink your urine, blood. All right, orange juice, things like that, lemon juice, it's got citric acid in it. I did a lab once where we measured the pHs of different soda pops. So people would bring in their favorite soda pop and measure their pHs, and they were around the 3 range. And then your really nasty acids, battery acid being like sulfuric acid, right? If you're working on your car and you got an acid leak in your battery, that's nasty stuff. But anyway, that's the pH scale. Just remember, pH is less than 7 is acidic, greater than 7 is basic. That's a heck of a lot easier than going comparing hydronium ion versus hydroxide concentrations. There you go. There's our review on pH. Let's get into some juicy equilibrium calculations for acidic and basic solutions. Nice!